All right, good evening, everyone, and welcome to the first ever Astronomy on Tap Scobee Education Center collaboration for Astronomy on Tap, the virtual edition. I know we were having an event that we had planned for Earth Day with Astronomy on Tap, and then COVID hit, and then a lot of events across the entire globe got canceled, and all of us have been learning to adapt from that. So now we can officially meet virtually for Astronomy on Tap to toast to the universe, to learn something amazing. So tonight with us, we have Dr. Vincent Hue from Astronomy on Tap, and he's going to share with us information about the Juno mission. But before we get started, I want to thank Tracy Becker from Astronomy on Tap and Swery for helping arrange this, as well as the wonderful group from Astronomy on Tap that they're willing to collaborate with us so that way we can host this for everybody here that is kind of stuck at home and wants to still hear amazing facts about our universe. Also for the Scobee Education Center team for helping collaborate with us and to get everything set up. We hope that this is an amazing event and we hope to host more in the future. But now allow me to introduce to you our amazing guest speaker, Dr. Vincent Hue. Dr. Vincent Hue is a planetary scientist working at Southwest Research Institute here in San Antonio. So we are literally touching the cosmos from our own backyard. And he specializes in the study of giant planetary atmospheres and the systems of their moons. And he's going to discuss to us the Juno mission and what his part is and what awesome new things we can learn. So if you have your favorite snack or drink, my personal poison is Coke. Leave a hashtag and post it up on Facebook to Astronomy on Tap and Scobee Education Center. We would love to see what your favorite snack or drink is as we toast to the universe and check out this awesome presentation. Dr. Vincent Hue, please take it away.
All right. Good evening, everybody. Okay, let me share my screen now. All right, all right. Okay, can you guys see my screen and my mouse too?
Yes.
All right, awesome. Good afternoon or good evening, everybody, for this first ever, as Michel says, Astronomy on Tap virtual edition. Just a little reminder for some of you that may or may not have been to Astronomy on Tap. We usually gather, well, when there is not a pandemic hitting the Earth, we usually gather once a month in this place called the Blue Star Brewing Company, where we discuss about the latest discovery about space research and astronomy. So you can see here some pictures of some of the gathering we had in the past with amazing speakers. We've been organizing about 22 events, 23 events so far. But when the pandemic hit, we decided to take a break. So thanks to the Scobee for helping us or participating and collaborating with us to start again this amazing events that we have. Astronomy on Tap is not local in San Antonio. It's a global, it's a worldwide organization. It was initially started around New York. And this map shows you the location in the world of all the ongoing Astronomy on Tap right now. I don't have the updated version for the COVID times, but I hope many events went virtual like this one. The Astronomy on Tap in San Antonio is actually a team of amazing people, and actually I miss seeing them. This is why I put this the picture of one of our gathering in the past. And so this is a full team of people working and helping with Astronomy on Tap. We have Christina Ray, Lizeth, Adam, myself, Brian, Samantha, Tracy, and Chris helping for this event to be possible. And of course, thanks for the Scobee again. All right, so tonight I'm going to discuss about the exploration of Jupiter, and most particularly with the latest and most recent spacecraft that is currently orbiting Jupiter, that has been there since July 2016 in the Jupiter system. This spacecraft here is named Juno. It has 3 large solar panels that you see here, and it's on this very particular orbit, a very elliptical orbit drawn here on this graph that brings the spacecraft extremely close to the planet. So Juno is really amazing, and it's been discovering a lot of new things about Jupiter, and I'm going to share some of those things with you tonight. Obviously, this is Astronomy on Tap, so don't forget to cheer, and virtual beer or the drink of your choice for all. And don't forget, it's only for 21 plus only. All right, so let's do a little recap about Jupiter. Jupiter is the biggest of all the planets in the solar system, and you can actually fit about 11 times the Earth within Jupiter. It is also the most massive one. Jupiter is about 300 times more massive than the Earth. So it's really a giant planet. And the main differences between Jupiter and the Earth is that Jupiter is mostly a gaseous planet. 99% or more is composed of gas, which is hydrogen and helium. But when we, as a scientist, when we take pictures or data of the planet, what we like to do is to make maps. So let's make a little map of Jupiter. You can see Jupiter is very different from the Earth. It's mostly what you see, what the different parts of the planet you see are mostly different layers of cloud with different colors. This is the equatorial region of the planet. This is the polar region. And we've been observing this planet quite a while. So we understood, we kind of have a feeling of how this planet functions. This video, for instance, was taken by the Cassini spacecraft as it flew by Jupiter in the year 2000. And it showed the extreme complexity of the atmospheric circulation of the planet. It's mostly composed of east-west bands of wind. The white one, we call them the zones, and the orange or the reddish one, we call that the belts. And they flow at a very impressive speed. So again, Jupiter is mostly gaseous, but has some trace species, such as ammonia, water, methane. And this is a trace species that actually colors the cloud on the planet. The white cloud that you see here is actually the uppermost or the highermost cloud into Jupiter. And then you have different layers of cloud. So on top, you have the white ammonia cloud. And ammonia has this particularity to react with the light coming from the sun, with the UV light coming from the sun, which degrade and through chemical reactions lead to more different molecules. And you just need a tiny fraction of those molecules to actually give different colors to the cloud. So ammonia, by degrading, give rise to different colors of the cloud, like the orangish, yellowish color that you can see. So Juno is actually answering a few questions. Some of them are: what's inside Jupiter? How does Jupiter's atmosphere work? How did Jupiter form? And what is Jupiter's magnetic environment like? So tonight I'm gonna explain, or I'm gonna talk about three different topics. I'm gonna explain a little bit about Jupiter's magnetic environment. I'm gonna talk about how you guys online or everybody can become a part of this mission to become a citizen scientist. Yes, this is possible. So I'm gonna explain what's the process for that. And in the end, I'm going to talk about what are Jupiter's cloud made of, which is one of the latest and most recent discovery made by the Juno mission. Okay, let's start with Jupiter's magnetic environment. So Jupiter, being the most massive planet, has also the most massive and strongest magnetic field in the solar system. And you can see this magnetic field as kind of a protective boundary, protective barrier for the particles coming from the sun, what we call the solar wind, which creates this kind of rounded shape in the direction of the sun, because the sun is kind of pushing on it with its particles. But not only it offers a protective barrier for those particles, it also traps some particles inside this boundary, inside this magnetosphere, what we call. And those particles, what we call the radiation belts, are very dangerous for any human being or spacecraft that we build. So we need to be very careful when we want to send something in the Jupiter system. And I'm going to explain a little more about that. And one of the consequences of having such a strong magnetic field is also that Jupiter has very bright aurora. Also, I'm going to talk about that. But for Juno to achieve some of its science goal, it needs to get very close to the planet, because it wants to investigate the interior of the planet and the atmosphere. Therefore, the closer you are, the more resolved the pictures you take, and the better is your understanding in the end. Which is a problem, because Jupiter's radiation belts are fairly close to the planet. So we had to design an orbit with Juno that actually allows us to get close to the planet, but don't get too close or too deep into the radiation belts. So the radiation belts, you can represent it this way. You can imagine like a donut shape around the planet. And with Juno, we are actually orbiting the planet such that we go between the planets and the radiation belts. So we just get a little bit of exposure to those deadly radiation, and then we escape pretty fast after we took all the data we want. And you can see also that the orbit of Juno is varying from the first orbit we were doing, which was in 2016, and the 31st orbit we will be doing sometimes around next year. Right now we're at orbit 29. We did orbit 29 last week. So in addition to have very strong radiation belts, Jupiter has pretty powerful and bright aurora. So an aurora is just a consequence of having a strong magnetic field. Earth has aurora that we can observe. This is, for instance, a video taken from the International Space Station. I'm going to play it again. Beautiful images of video. For Jupiter, we can actually observe the aurora. But the only difference is that Jupiter's composition is widely different from the Earth, and therefore you cannot see it with your eyes. You have to build a specific telescope to be able to look at those aurora. Those aurora are mostly emitted in the UV. And so this is an image taken by the Hubble Space Telescope. So that is currently orbiting the Earth, looking at Jupiter. looking at a small region over Jupiter's north pole. So Jupiter's north pole is around here, and this is like the northern hemisphere of Jupiter. Since we observe in the UV, we can't really see all the optical details we can see otherwise, like the clouds, different colors, etc. And one of the results of Juno, one of the opportunity given by Juno is that we can actually now look at those things, not from a very slant angle like we could do from the Earth, but from really sitting on top, so to speak, the North Pole and behind the planet too with Juno. And this is what was taken by Juno. So this is an image taken by Juno. The sun is in that direction. The North Pole of Jupiter is around here, and we're actually looking straight down the planet. So this kind of configuration we can see it from the Earth, because the Earth is somewhere around orbiting the sun. But one of the things that Juno gave access to is actually looking at the aurora, but on the night side of Jupiter. So when the aurora is tilted toward the outer side of it. And one of the big discovery was to show that some part of the aurora actually shuts off at night. And this is a pretty big result, and was, by the way, made by a scientist that lives in San Antonio. He also works at Southwest Research Institute. And why it is important to understand the magnetosphere of Jupiter and the aurora? Well, the thing is, there's a lot of good and interesting things into the Jupiter system. Some of them are the main moon of Jupiter, the biggest moon, such as Io, Europa, Ganymede, and Callisto. Of course, this graphic is not to scale. The moons are way tinier than that. But the thing is, those moons are very interesting, for instance, for the potential for habitability or for finding life. Those moons are very interesting and are the topic for future investigation. For instance, the European Space Agency is going to launch a spacecraft named JUICE that will be orbiting the Jupiter system near the year 2030, and Southwest Research Institute is involved in that mission too. And NASA is currently designing or building the Europa Clipper mission that will be focusing mostly on studying Europa, also near the year 2030. So we might have two spacecraft around that year or over that decade in the Jupiter system. So those are two future missions. So that's why the work that Juno is doing right now is crucial for understanding better the environment and how we can access those moon. All right, so now let's switch. Let's leave off the magnetosphere and go look at the atmosphere of Jupiter. I'm going to talk about how you guys can be involved in the Juno mission through the JunoCam experiment. So JunoCam was actually a camera that was added later on the spacecraft right before launch. And that allows us, every human being on this planet, to be part of the Juno mission. The only thing you have to do is to register on this website, missionjuno.suri.edu. And you can actually you can participate in the planning of the observation, in the suggestion for the different observation sites, and also in the data processing of those images. So over the next 2 or 3 slides, I'm going to show some of the work done by those citizen scientists that took the data as it was taken by the JunoCam and processed them using, for instance, Photoshop or other photo software. So this one, I like it particularly, was made by this citizen scientist named Bjorn Johnson, because it shows the what your eyes could see if you were to go to Jupiter. Most of the images you see are actually, the contrast is enhanced. Therefore, if you were able to go with a spaceship all the way to Jupiter, this is what your eyes could see. So it's a little more pale than what you're usually used to. But of course, you know, when you give raw data to someone, the first thing they're going to do is to crank up the volume, not the volume, but the contrast, of course. And this is, for instance, one of the another images that was taken by JunoCam, processed by another citizen scientist, which shows, so you have here the North Pole, and you have here the equatorial region of Jupiter. So it's seen from a different angle. And you see that the atmosphere of Jupiter is extremely complex. You know, there is, as I said, there was Jupiter is composed of bands of winds flowing in opposite directions, and at the intersection between those two, a lot of turbulence is generated, a lot of vortices, turbulence is generated. So it's a very complex atmosphere. And another one that I'm going to show, this one was made by Gerald Eichstadt and Sean Doran, which shows, so this is the polar region of Jupiter. The equator is around here. And you see this blue hue that is around the higher latitude, so around the polar region, that is actually real. The contrast is just a little bit enhanced, but it's actually real. And it's caused by some of the trace species I was talking about, namely the methane. All right. And so in this last part of the presentation, I'm going to talk a little bit about some of the latest recent discovery concerning Jupiter's cloud composition. So in addition to Juno, there is this big campaign that people are running with the Hubble Space Telescope that are looking at Jupiter at the same time as Juno is looking at the planet, so that we can have double information, or sometimes more than double, because there is a synergetical approach to this. And so we can look at different parts of the planet with the two instruments with different angles and get more information out of that. So this images was taken by Hubble Space Telescope. And at the same time, Juno was looking at this particular region here. This particular region is actually a giant cyclone in the northern hemisphere. And so if we overlay the data taken by Juno with the data taken by Hubble Space Telescope, you can appreciate the difference in how great it is to go there and take pictures from up close. So if we zoom in again, this is the Juno images, Juno Cam images, and this is the Hubble Space Telescope. We can zoom in again, and this giant cyclone is about the size of the US, more or less, or even a little bigger than the US. So it's a giant storm. All right, and this kind of storm, we've seen them many parts of the planet, and they are actually extremely important. And I'm going to explain you a little bit why. Those storms are actually a giant convective storm that modify and affect the composition on Jupiter, the composition of trace species. So what's happening is that when those giant convective cell forms, they suck in some ice particles, because this, Jupiter is cold, so this is the altitude where most of the water condenses. So they suck in those ice particles, and when they raise in the convective cell, they actually can melt with ammonia, which is located a little bit higher, and then form what they call people from the Juno team, for instance, Tristan Guillot, named a mush bowl, because it's kind of a mush bowl like. They are mixed ammonia and ice, and those mush balls, when they raise in the atmosphere, they grow in size by grabbing more and more ammonia and water ice. And when they reach a certain size, they have to fall because of gravity. They cannot grow up to a certain size. And when they do fall, they go again through this region where they form an ice crust around this mush bowl. And this ice crust kind of captured the mush bowl and deliver the mush bowl down into Jupiter's atmosphere. So it's a pretty big result, because we better understand how Jupiter's work. And there was a big discrepancy. We know for many years, we didn't know, when in this region where we were probing with our instrument, we didn't know where the ammonia was. And that was a big question since a few spacecraft ago. So this shows that the ammonia was actually captured and delivered down in the atmosphere. So those storms are pretty important in controlling some of the composition of the trace species on Jupiter. All right, so that's it for me tonight. The summary, so I've been talking about Jupiter's atmosphere, which is more complex and turbulent than we previously thought, because we have more detailed observation now, thanks to Juno. I talked a little bit about the Jupiter's magnetic environment and how it triggers the brightest aurora in the solar system. I also talked about one of the Juno results, which showed that some of Jupiter's aurora shuts off at night. And I also talked a little bit about how you guys can get involved into to be part of the Juno mission as a citizen scientist with the GenoCam experiment. Of course, I just had 15 minutes today, and so I couldn't address all the questions, all the things I could talk about, because Juno is actually addressing way more questions than that, such as where is Jupiter's strong magnetic field from, or does Jupiter has a core, and how big is the core, and also how are the moon interacting with Jupiter, which is also very interesting and that Juno is addressing. So thanks you guys for your attention, and I'll be happy to take any questions, and cheers to Astronomy on Tap and Space and Scobee Center, obviously.
Well, thank you so much for that wonderful presentation. I know I learned a lot from that presentation. I look forward to checking out the citizen science myself. So for you folks that are here on Zoom, we have a Q&A button. So just type in your question there and I'll be happy to read it off. And so that way we can get some expert advice on some of these unique types of questions. Also, if you're on Facebook, leave it down in the comment section. Fire away. All right, so I have the first question. It's from Luis. He asks, it is expected to find the same molecule of phosphine found in Venus recently?
Yeah, well, actually, we can measure trace of phosphine I mean, phosphine is pretty much like ammonia, except that you switch one of the nitrogen atom for a phosphorus atom. And there is phosphorus. The thing is that Jupiter is a very reducing atmosphere. Therefore, if you leave an atom, it's going to grab all the hydrogen around it. So that's why if you leave some phosphorus, it's going to grab the hydrogen and it's going to make pH3, which is phosphine. So yes, there is trace species, but on Venus it's a very different topic because the atmosphere is very different, obviously, than Jupiter.
All right, next question from Alicia. She asks, why do the auroras shut off at night?
That's a very good question, and I think everybody in San Antonio would be, well, in our team would be happy to have the answer. We don't know, actually. We're trying to come up with different interpretation. One of them might be that when the aurora is oriented towards the day side of the planet, the sun shining through it allows more motion of charged particles in the uppermost atmosphere, the ionosphere, which would trigger more aurora in a way. Or the other explanation might be that there is something going on in the back of the if you want, the back of the magnetosphere, what we call the magnetotail, that is going on that we haven't figured out yet. So the magnetotail is so you have the sun, Jupiter, and the magnetotail is behind the planet.
All right, next question comes from Maria Stofhoff, and she asked, have the citizen scientists made any great discoveries?
Yeah, definitely. Just to understand the vorticity in the atmosphere of the planet. I mean, Juno was didn't consider GenoCam as a science instrument initially, and now for the extended mission that we're writing up for NASA to get extension, because right now NASA is funding us until the 31st orbit, which is going to be sometimes around next year. We're classifying GenoCam as a science instrument because it made a lot of discovery about Jupiter's atmosphere, the composition, the storm formation, and the cycle of the elements in the through those storms. So yes, definitely.
Okay, so we have another question from an anonymous contributor, and they said, what is the point to learning more about Jupiter compared to the other planets?
Well, the approach is not to leave out one of them. I mean, Jupiter is very important in many aspects, and it sounds like Jupiter is also, well, first of all, Jupiter, when you think about the formation of the solar system, Jupiter was the one who formed. And we think that the formation of Jupiter and the migration of Jupiter, because Jupiter didn't stick in that place during the formation of the solar system, it moved around. We think that it had a profound impact in how it has shaped the inner solar system, how the different inner planets, so like the rocky planets, are the way they are now. We think it had effect because when it moved, it also pushed a lot of things such as asteroids, and we think that when it moved, it has triggered some delivery of different composition. Maybe it might have brought water to the Earth. We're not 100% sure yet, but so Jupiter is super interesting to study. Among the four giant planets, it is also the most accessible one because it's pretty close to Earth compared to Saturn, Uranus, and Neptune, and has some great moon too. The moon are super fascinating. I mean, Europa just by itself is incredible. I haven't talked about Io too much, but Io is my favorite moon. And just just on Europa and on Ganymede, on each of those moons, there is more liquid water in the underneath or subsurface ocean than all the liquid water we have on Earth. So it's just insane to think that we should go there and study this place and see if there is any sign of life or any sign of very complex molecules.
Okay, we have a question from a young audience member. From a particular 5-year-old, they said, "Why is Jupiter so big?"
That's a great question. So the solar system formed from a giant cloud that probably didn't look like the cloud you have behind you, Michelle, but it's just a giant molecular cloud in the universe. And what came out from this cloud is first proto baby sun at the center, and the leftovers of this baby sun formation was a lot of dust and a lot of gas, and so then this dust kind of collapsed into different like little bubbles, if you want, and those bubbles grew and grew. Those what we call planetesimals, they grew and grew. Those small planets, they grew and grew because there were a lot of leftovers from the sun initial, the baby sun initial formation. And it led, the first planet who grew the most was the biggest one, and it was probably Jupiter. So that's why I think Jupiter was the one who formed first. So it had more time to grow and grow in size until there was no leftover to grab to make to grow in mass.
Awesome. Another question from Luis. He says, "Does the heat from the core could support primitive life form as we know?"
The core from Jupiter, I mean, the life as we know need probably a breathable atmosphere, a solid surface, a Netflix account, and no, I'm just kidding. But no, I don't think life could sustain just from the heat from the core. The heat from Jupiter's core is definitely something that is very important. But we can't really live on Jupiter. I mean, there's no way. We need. We could probably live, but with a lot of effort on the Galilean moon. But on Jupiter, there's no way.
Question from Beatrice. She asks, "Why does Jupiter have 4 moons?"
Well, Jupiter has actually, if I remember correctly, around 78 moons so far, and we're still counting. So it's just turned out that it has 4 big moons, that's for sure. And then a lot of other moons are way smaller. It's just the way Jupiter formed. We think that some of the moon was probably could have led to planets, but then they got captured into Jupiter's gravity and they ended up as a moon of the planet. Yes, that's so Jupiter don't have any like specifically full moon. It has way more than that. And it comes from the fact that Jupiter was a big planet and it grabbed a lot of things when it formed, and probably later too.
Next question comes from Tracy Becker. She asks, for how much longer will Juno be studying Jupiter?
So the nominal mission, which is what NASA allowed us to study to found us with Juno, is gonna be ending sometimes next year. But we'll still have fuel to go, so we could still extend the mission. But of course, when you do that, I mean, you're using public funding, so you have to show that what you're gonna find out what you're gonna discover with this extension is worth paying for. And so right now we're gathering all the facts and discovery that have been made and what will be made with the extended mission, because as I showed, the orbit is changing over time. So in that extended mission, we'll have access to different parts of the Jupiter's environment. For instance, we'll be flying by the moon. And so this is very interesting because we're going to send 2 more spacecraft, like in this decade, towards the Jupiter system. So flying by those moon will bring some tiny bits of data that will help those future missions to either find, to learn more about what they're going to study, or find more different sites that will be of interest.
All right, next question from Marina. She asks, is Jupiter's magnetic field able to reach other planets?
The answer is yes. So it's just a giant, it's just crazy. So on the anti-sun direction, so you have the sun, Jupiter, so the sun is pushing on this side, but on the other side, the magnetic environment is stretching very far, and it's actually stretching all the way to the Saturn system. So it's just insane to think about that. Jupiter can reach all the planets, but of course, the further out you are from the planets, the less important is the magnetic field, and it turns out Saturn has an important magnetic field too, and not as great as not as strong as Jupiter's, but still important.
I got a question from here on Facebook. It asks, will the SWIRI Juno team be involved with the European Space Agency team preparing for JUICE?
Yes, that's a great question. So the Southwest Research Institute team in San Antonio is actually involved in those 2 missions that I talked about, the Europa Clipper. It is building 2 instruments on the Europa Clipper, and it's involved in JUICE too. It's building mainly 1 instrument, and I think they're building some parts for different other instruments. So yes, we'll be very, very involved and very busy in the next probably 20 years. Yeah, when you think about those time scale, it's just crazy. But yeah, so great question.
Next question actually comes from a group of Girl Scouts, and they would like to know, what would you suggest for them to do with the citizen sciences, and what would make a good citizen scientist?
I'm sorry, I didn't hear the full question. You kind of cut at one point.
Okay, let me pull up the question again. A group of Girl Scouts is asking, what do you suggest they do to be citizen scientists, and what would make them a good citizen scientist?
That's a great question. I'm not sure I have an easy answer to that. I can tell you that with the GunoCam experiment, not only you can do science, but you can do art too. And a lot of people came up with artistic creation using some of the picture taken by Juno and merged them into with their artistic process. And they came up with incredible creation. And it's for me, it's so cool that people can take that and make art with it. It enhanced the reach of those pictures taken at Jupiter. But in terms of science, I think I would have to think about that. I'm not sure. There's a lot of great science that is done, but I don't, not particularly involved with the Juno cam. But I think just getting online and seeing the instrument, how it's taking pictures and the different part of Jupiter, you might be able to understand better what's the need for the science community to come up with those pictures. So.
All right, so the next question we have is, how many layers of clouds are there on Jupiter other than red and white zones?
So we're pretty sure there's 3 uppermost layer. So you have ammonia, and then you have this this cloud that I can't even remember the name, but I know the chemical compound, which is NH4SH. So there's some hydrogen, there's some nitrogen, there's some sulfur. We think this is what gives the color. And then below that you have water. But then below that, this is kind of the unknown. And I think I might have a slide to explain a little bit that. I don't know if you can see my screen. No, I probably have to share again.
Yeah. Oh, technology.
Yes. So, that was the interior model of Jupiter before Juno. So the Earth is right here. We have a core, we have a mantle, we have the crust and the atmosphere. On Jupiter, before Juno, we thought that Jupiter had a 15 Earth mass core made out of rock, metals, and heavy elements. Then that it had this metallic hydrogen layer, and then this liquid hydrogen, and then gaseous hydrogen layer. But Juno allowed us to revise completely that, and we realized we're very wrong. But we don't know how wrong we are still. We think that now there's still a dense core in this model using the Juno data, but we think now there's kind of a mixed layer of rocky and heavy element and this metallic hydrogen. And then you have where the water, sorry, the helium is condensing here. So deeper down, you might have not only those 3 clouds layer I talked about, but you might have those kind of helium cloud layer. And then the molecular hydrogen, what we know. But the thing is, this is a difficult problem because we can only reach the not even the 1% of the whole radius. So all of that is inferred from gravity measurements, which are indirect measurements. We did once send a probe, the Galileo probe, that just touched the outermost layer and stopped functioning after a while because of pressure and temperature that was too high. So there might be other cloud deep inside the planet, but we don't know for sure. There might be cloud with a very widely unusual composition for what we know on Earth, like rock cloud, for instance, but we don't know. Yes, so that's my answer to your question.
All right. Next question is how long does an instrument like Juno take to design and build?
So that's a question, an interesting question. I would say it took about 6 years to build the spacecraft, to build the instrument. But of course, when you, it's about 5 to 6 years, I would say, from the moment where NASA says, okay, I like what you're proposing us. Your instrument is good. It's gonna revolution. It's gonna like change the whole field. Until the moment where you can launch, it's about 6 years. But before that, you need to do a lot of work on your own by developing instrument. So you need to already have kind of a good idea of what you're going to propose NASA. So you need to do internal development, like basically building prototypes of what you're going to propose to NASA, and then you propose that, and then from that moment up to the launch, it's about 5 to 6 years. It depends on how big the project is.
Excellent. Okay, so the next question we have is, have observed meteor strikes on Jupiter had any impact on the weather?
That's a very good question. So I wouldn't say meteor, but I would say cometary impact. Because of course the small meteor, I'm not sure we can detect that because we're pretty far from Jupiter. But we've seen large cometary impact in the past, and they actually affect. They must affect the weather by a huge amount because they bring a lot of material. So like back in '94, there was this comet called the Schumacher-Levy 9 that orbited around Jupiter. It didn't orbit at first around Jupiter, but it got pretty close to Jupiter. And when it did get close to Jupiter, it kind of dislocated in different fragments. It was still orbiting Jupiter, and all those fragments fell on the planet, on different part of the planet. You could look it up online, the Schumacher-Levy 9 impact. And even like 20 years ago, we can still see remnant of the things that this comet brought. Comets have a lot of water, and Jupiter's upper atmosphere have very little water. And so it brought a lot of these molecules into the planet that we can still monitor 20 years ago. Because the water you put high in the atmosphere takes time to move around and settle down to level like deep down into the planet. So yeah, it has huge impact on the planet.
All right, next question. Does Jupiter's magnetic field benefit other planets?
That's a very good question. That I said earlier that the magnetic field in the anti-sun direction can reach all the way to Saturn. Of course, you have to have Saturn aligned with Jupiter so that it can fly through the tail of the magnetic field. So I'm pretty sure it must influence. I'm not aware of any specific fact I could give you, but yeah, it must be something to study.
Well, and then a follow-up question is that, okay, since it can reach out to Saturn, how does it affect Saturn and its moons? And what happens when Jupiter's magnetic field, when the two magnetic fields collide?
That's a very good question. So as I said before, the further out you are from a body that has a magnetic field, the weaker is the field. So when you get close to Saturn, sorry, the field, the dominant field might be the Saturnian, the what we call the Cronian, the magnetic field of Saturn. So that would be the one dominating. But the thing is, Jupiter has a lot of things inside the magnetosphere. It has a lot of charged particles, and those can be spit out and channeled through the magnetotail towards Saturn. But I'm not sure what would be the effect of that because it's a long distance, and those things might be diffusing over time. So that's a good question, though.
All right. Next question is, what do you expect to learn from deorbit?
Deorbit? Well, deorbit is not actually going to be a deorbit. It's going to be a crash that we're going to do.
I think that's what they're probably asking is like, okay, so it's going to crash. What do you hope to learn from crashing into the planet?
Yeah.
Kind of like how the Galileo probe was put in through Jupiter's atmosphere a while back. So are we going to learn anything from Juno going into Jupiter?
Well, I mean, Galileo was designed to measure temperature, density, composition as it went down into the planet. Juno is not designed for that, but we can still get some information like close-up pictures, magnetic field measurements, because Juno has a ton of instruments that are designed to measure magnetic field and particles. So those things, as you get close to the planet, for instance, measuring the particles in the ionosphere of Jupiter. And one other thing we could do is also the radio measurements. So transmitting a radio signal to the Earth and getting the response back and measuring like that the ionosphere of the planet. So we could do those things. We haven't thought too much about the orbit, but that's a very good question. But we don't have any mass spectrometer to measure different composition like Cassini had. And also it's a challenging problem because you have to, since it's going to be a last crash on the planet, you have to make sure you can transmit the information before crashing on the planet. Otherwise, it's lost forever. So.
All right. Next question. I know you kind of put it in your presentation that it's a big question mark, but maybe you could try to take a stab at this. It says, is there a solid surface on Jupiter, kind of like the Earth's crust? Is there like a liquid core of some kind? I know I learned it was like possibly liquid hydrogen of that nature.
Well, I mean, liquid hydrogen wouldn't make a surface. And plus, most of the, I can probably share again my screen if you don't mind. So, I mean, it depends what you call the surface. In the pre-Juno interior model of Jupiter, we thought that Jupiter has a rocky core, but there, I mean, you're at temperature that are about 20,000 Kelvin with a huge pressure. And so I doubt you can have like a solid surface, a nice and gentle solid surface like you would have on Earth first. And then the post-Juno, I mean, still working on this, but the gravity data we got from Juno tend to suggest that the core might actually, it might not be like a clear separation between the metallic hydrogen and the dense core. It might be more like a gradual diffusion of, if you want, the diluted core. This is the proper name that we now use. Gradient of denser in the center, and then towards lighter element all the way to metallic hydrogen right here. So there is, I mean, there's literally no surface. Like, so we think right now. So yeah, so that's my answer. I'm gonna stop sharing again.
All right, are there any more questions? Any more questions? I had a bunch of good questions.
Yeah, a lot of good questions. Thank you, guys. And thanks to the Scobee, thanks to Adam for setting up the live stream also. Yeah. So any last questions, feel free. Maybe you could advertise also for the next events that we have. I don't know if we talked about that.
Oh yes, absolutely. The next event that we're hoping to have, in fact, if you guys want to mark your calendars, this Saturday on the 26th is the International Observe the Moon Night. So we're going to have a couple of speakers, Dr. Hooper from LCATS, which is the Lunar Caves group, as well as Lizeth, I'm going to mispronounce her name, Miss Lizeth Magana, thank you.
Yeah.
She will be doing presentation on ice on the moon, which will be really interesting. So if you want to listen to their wonderful presentations, you're welcome to join us for our presentation of International Observe the Moon Night on Saturday the 26th. And hopefully sometime in October, we'll have another Astronomy on Tap Scobee collaboration.
Yep. let's work with that. Yeah, that'll be fantastic. Okay, thank you guys, and have a great evening. Stay safe.
Yes, stay safe, stay healthy, never stop learning, and cheers, everybody. Have an awesome night.
Cheers, guys.